Hello everybody and welcome to 21st lecture of MHM 42780. In our previous lecture we solved one example together by using Epsilon Ntu Method, and today we are going to use Lmtd Method and see if we are getting the same results. Just to remind what we have done during the last lecture, I'm just going to write some of the information that we had from the question, as well as the values that we have calculated by using Epsilon Ntu Method. So first we after going through the question itself, we realize that we have lots of information basically from the question itself. So if we want to write it down here, we realize that our cold fluid is oil and our hot fluid is ethylene glycol. We also realize that we have information regarding the input temperature of cold fluid, as well as output temperature of cold fluid, input temperature of hot fluid, output or outlet temperature of hot fluid. So just write it down. It's 10 degrees and Tc out is equal to 70. Inlet temperature of hot fluid is 110, and outlet or output temperature of hot fluid is 90. We also from the question itself, we have the thermophysical properties of ethylene glycol. It's given. Sorry. So it's rho is equal 1062. Sorry. Mu is equal to 2.499, 10 to the power of minus 3. I'm just writing it from the question itself. So we didn't do anything. We are just writing down the information that we have from the question. 0.262. Also have Cp here. We put H 2742 joule kilogram Kelvin, and Prandtl is equal to 26.12. But for cold fluid oil, we said that the properties can be written from table A13, but at what temperature? The average temperature between 70 and 10, which is 40. So from the table we just write it down here. Okay, so those information was provided, so the majority of them was provided from inside the question. Just one property of oil was written from table A13 at 40 degrees. We also knew that the m.c is equal to 4005 kilogram per second, and by applying the energy balance we could find 8.7 kilogram per second for hot fluid. Okay, mass flow rate of cold fluid, oil, mass flow rate of hot fluid, ethylene glycol. How we find this one? This was given, but this one after applying the energy balance. By this information we said that okay, there are two different methods of solving the questions related to heat exchanger. The first method is Lmtd, and the second one is effectiveness or Epsilon Ntu. Lmtd is based on this correlation, that is Q dot is equal to AS U F delta T Lm Cf, and Epsilon Ntu is based on the number of thermal units, which is equal to AS U C min. Okay, so we realize that okay, the question is asking us to find number of rho. So to find the number of rho, we need to find AS first. So in those two cases we said that okay, it doesn't matter which method we are going to use. First we need to find U, which is overall heat transfer coefficient. So to find or calculate the overall heat transfer coefficient, we said that okay, overall heat transfer coefficient can be easily calculated from this equation. Divided by 2K plus 1 HO. The HI was given 2500, but we are not that lucky always that this H is given, so we need to calculate that one, but we were lucky in this case, it was given. We have all those values. We also have K for convection heat transfer coefficient of outlet. We just know that okay, it's a very classic convection heat transfer problem. So in order to find the heat transfer coefficient, first we need to find Reynolds. After finding the Reynolds, we need to find Prandtl. By having Reynolds and Prandtl, we need to go and look based on the range of Reynolds and Prandtl and the situation to find the right correlation to calculate Nusselt. After calculating Nusselt, we can find heat transfer coefficient. So we did the same procedure. We calculate Reynolds to be 1211. We also said from the information that we had for the thermophysical properties of hot fluid, which was ethylene glycol, we said that okay, Prandtl is equal to 26.12. But by having all those information, we find a correlation for Nusselt, but we realize that that correlation needs a Prandtl number for saturation temperature at 40. We find that one as well, and by having all those numbers, we calculated Nusselt to be 57.76, and after that we calculated HO to be 605.3 watt square meter Kelvin. By having all those values, so we find overall heat transfer coefficient to be 478.4 to Kelvin. Okay, now what we did in our previous lecture, we said that okay, from this point we are going to use Epsilon Ntu method, and we solved the problem, and we find AS to be 18.38, and after that we said that AS is equal to pi DOL multiplied by NL multiplied by NT, but NT here is transverse row, which is equal to 14. So NL, which is the number of row the question is asking us, was equal to 33. Now what we are going to do today is we want to do everything by using Lmtd method and see if we are getting the same result. Why we are going to use the Lmtd method? Because if you remember previously I mentioned that there are two methods, and you can use both of them if you have all the information necessary, but sometimes you really cannot use Lmtd method, because Lmtd is you can use it when you have all the temperatures. I mean the inlet and outlet or output temperature of cold and hot fluids. But all the temperatures should be given as like values? No, sometimes by having just three values you can apply the energy balance and you find the fourth temperature which is missing. But sometimes even by applying the energy balance you cannot find all those temperatures. So that case, even if you are not comfortable with Epsilon Ntu, you need to use it, because otherwise you can't get any answer from Lmtd method. But in this case we know that we have all the temperatures, so let's try Lmtd method and see if both Lmtd and Epsilon Ntu are giving us the same final answers or final values. Okay, so let me just go back to our brainstorming and see what kind of information I need for Lmtd method. So for Lmtd, said that the basic equation will be UF counterflow. So we said that okay, this one from the previous steps, we have it to be 478.4. Correction factor, we don't have it. Delta TLM, when it's configuration of counterflow, we don't have it. AS is something that we are looking for, and Q dot we don't have it. Okay, so let's start step by step and calculate each of them, find them. First, we are going to start with correction factors. Correction factor F. Correction factor, we said that okay, beside very simple configuration, always you need to have a correction factor. But in this case, we know that it's a complicated geometry, so for sure we need to deal with a kind of like a correction factor. But how we can find that correction factor? If we go to figure 11.19 of our textbook, we can see this basically figure section D, and when you read the description of this section D, you can see that it's for single pass cross flow with one fluid mixed and the other one unmixed. If you remember, in our previous lecture, we said that it's more or less the same case, because in this case it's the same. If you go back to the question itself, or here, you can see that the oil is unmixed. Why? Because it's going into the tube, and Eg is mixed. But here there is no mention about cold fluid be mixed or hot fluid be mixed. So in both cases we can use it. So in order to use this figure, first we need to find or calculate R and P. As you can see here, R is defined as capital T is the temperature of hot fluid. 1 means inlet, 2 outlet. Okay, so inlet temperature of hot fluid minus outlet temperature of hot fluid divided by cold outlet temperature of cold fluid minus inlet temperature of cold fluid. So I'm just going to put the values here. 110 minus 90 divided by 70 minus 10. So what we are going to have is 0.33. We also need to calculate P as well. So as you can see here, P defined as the outlet temperature of cold fluid minus the inlet temperature of cold fluid divided by inlet temperature of hot fluid minus inlet temperature of cold fluid. We just put the values here. So it will be 0.6. Now we need to go back to this figure and see if we have those values. 0.6, that's fine, we have it, so it's this line. Everything will happen on this line. So very simple. But for R, we can see here that we have for 0.2 and R 0.4. But how about 0.33? We don't have it, but we can have a kind of estimation here. So let me just, maybe if this is some kind of like a estimation, it's closer to 0.4 than 0.2. So here is R is 0.33. Okay, so 0.6, basically that's our point. The point that the line P equal 0.6 will cut the line or curve R equal to 0.33. So this value, correction factor, is going to be 0.95. Okay, now we sorted out one of those values. Now we have here, so I'm just going to write it, 478.4. We also have F, which is 0.95. Now we need to calculate delta TLM, but for counterflow. We said that it's very easy. In any case, is delta T1 minus delta T2 divided by ln delta T1 delta T2. But what was the difference is, like, for different configuration, delta T1 and delta T2 are different. So we said that the best way of not making any mistake is just like using very simple figure. Just put inlet temperature of hot, outlet temperature of hot, and we just like simply inlet of cold, outlet of cold. Here is delta T1 and this one is delta T2. So basically, delta T1 is equal to, but it's for counterflow configuration, minus T O, and delta T2 is equal to O minus T I. Let's just substitute the value, minus 70, which gives us 40, by 90 degrees minus 10, which gives us 80. If we want to put it, so delta T M is equal to 40 minus 80, C divided by 80C, which gives us the value of 57.71. Okay, now let's go back to the here. We also find delta T M for counterflow, which is 57.71. Now what the only value that we need is Q dot. Okay, how we are going to calculate the Q dot? So it's very simple, because we know that from the energy balance, Q dot is equal to cold Q dot hot fluid, by neglecting all those energy losses between the hot and cold fluid. So we can either use this correlation or we can use this one. I minus T O. So I use the second one, so 8.7 multiplied by 2742. The answer will be 477,108 watt. Okay, now let's go back and write it here, and we have Q dot is equal to 477,108. Okay, now we have all the values, so simply we can calculate AS. So here, let me just write it down. So this is Q dot divided by UFM counterflow. So if I just write all those values and calculate it, easily I can find the final answer. .71. So the final answer, AS, is equal to 18.19. Is Lmtd method, and if you remember from Epsilon Ntu, AS was 38, sorry. Very close numbers, and if we find number of rows, we can get to 33 numbers. So it's exactly the same as Epsilon Ntu values for NL that we calculated in our last lecture. As you can see, the results are exactly the same. Not exactly in terms of being exactly like 18.38. So of course different methods, especially in that case, the way that I have calculated the correction factor, you see that that might have a little bit of error here, because we just estimated, and we didn't really know where r equal to 0.33 is located. So with a very good assumption, we can say that AS, if we use Lmtd method, will be equal to 18.19 square meter. Okay, but we also know all those uncertainties related to correction factor. Okay, and this 18.19 square meter is very close to 18.38 that we have calculated from Epsilon Ntu. Both methods give the same result. For you is the same. Doesn't matter which method you use, the final answer should be the same. If you do all the steps correct, you can't get completely two different answers from Epsilon Ntu or Lmtd method. At the beginning of this lecture, I mentioned that these two methods basically can be preferred in some kind of situations. For example, when all those values in terms of inlet and outlet temperature of cold and hot fluids are available, Lmtd method is very straightforward and easy method, because by knowing all those temperatures, you can easily calculate the delta TLM. You can also easily calculate or find the correction factor based on the configuration of heat exchanger. But you, of course, it's something different, and you need to calculate the overall heat transfer coefficient. But there are some situations that you don't have all those temperatures, and at the same time you cannot, by simply applying the energy balance, find all those temperatures. So in that kind of situations, Epsilon Ntu is the method to be used. Why? Because you don't have all those temperatures to be able to use Lmtd method. Okay, so I just did this example from two different methods to show you that how does it work, and you shouldn't see the different results, because sometimes we get that, oh sorry sir, I get a different result because I used Epsilon Ntu method instead of Lmtd, or I got a completely different result because I used Lmtd method, while for example memo is based on Epsilon Ntu method. Whatever method you use, answer should be the same. Okay, so that's let's solve another example here. It's question 11.125 of your textbook. It's saying that the shell and tube process heater is to be selected to heat water. So the Cp of water is given from 20 Celsius to 90 Celsius by steam flowing on the shell side. The heat transfer load of the heater is 600 kilowatt. If the interior diameter of the tube is 1 centimeter and the velocity of water is not to exceed 3 meter per second, determine how many tubes needed to be used in the heat exchanger. So it's again, first you need to find AS, and after that, after having or calculating that, you need to find the number of tubes. But just let's see what kind of information we have at the moment. Okay, now just let's write all the information that we have. We have the Cp of water, Kelvin. The temperature, you can see here we have the to be 20. We also have Tc out is 90. So do we have the inlet temperature of steam? No, we don't have it. Okay, what else do we have? Do we have we have a velocity here, 3 meters per second, not exceed. We also have something like 600 kilowatt, the heat transfer load of the heater, the heat transfer. Load of the heater, is 600 kilowatt. That's the information that we have. But what we use that heater to increase to generate the steam, and after that, so the heater gives the energy to steam, and after that the steam gives that energy to the water. Okay, so basically this 600 kilowatt is our Q dot. Okay, now it looks like that we have lots of information. We don't have any information regarding the inlet and outlet temperature of hot fluid, but let's say we have it for cold fluid. So Q dot C, which is equal to Q dot H, but C, we know that Q dot C is equal to 600 kilowatt, and it's equal to M dot C Cp C Tc out minus Tc in. Tc out, we have it, yes, 90 degrees. Tc in, cold inside, yes, we have inlet, yes, we have it, 20. Cp of water, we have it. Here is kilowatt, we can write it based on the kilojoule, kilogram Kelvin. So by having, and this one we just put it here, kilowatt. So we can find the mass flow rate of water. So mass flow rate of water will be equal to, we do all those substitutions, 4.19 kilojoule kilogram Kelvin, 19 minus 20, so we can calculate it to be 2046 kilogram per second, M dot C. the mass flow rate of cold fluid, here the mass flow rate of water. But let's go back and see what the question is asking us. It's asking the number of tubes in the heat exchanger. So basically AS is the problem here. But we have an issue here, because if you look at that, how we are going to find it, so we need to find U, which is the overall heat transfer coefficient. After, when we find U, we have the Q dot, so we need to find delta T Lm for counterflow and correction factor, but we can't use Lmtd method. Why? Because we don't have any of the hot inlet and outlet the temperature of hot fluid, so then we cannot use Lmtd method. How about Epsilon Ntu? Let's say we want to use Epsilon Ntu method, but we know that for Epsilon Ntu method we also need to find or calculate the heat capacity of cold and hot fluid. So we, on top of m dot c, which is we have calculated and is the mass flow rate of cold water, we need to have or be able to calculate the mass flow rate of hot fluid. Otherwise we won't be able to use it. Why? Because we can't calculate the small c, which was the capacity ratio. When we don't have a capacity ratio, we can't use any of those correlation from the table 11.5 to find the number of thermal units. So then what are we supposed to do here? If we go back to the question, we see that some of the information is given there. The inner diameter of the tube is given, and the velocity of water not to exceed, so the maximum velocity of water is given as well. So if you remember, it is very simple. You use it a lot in thermodynamics. So m dot is AC. You remember that? But here is like all, we can put it cold, or the velocity of water, this is cold. So m dot c, we have a 2.046 kilogram per second. The density of water, we have it 1000. We also can go to the table and read it at the average temperature between 90 and 20, but I just like to use 1000 multiply by 3 per second, and AC we don't have it. But what is AC? AC is total cross section area. So C means cross section area. Okay, so cross section area we can calculate, and it will be equal to 6.82 10 to the power of -4 square meter. So now how we are going to find AS? Good question. So AS, basically, first we say that number of tubes pi 2 divided by 4. Okay, So we need to find n. So basically n is equal to 4as pi d2. So n will be equal to 4 multiplied by 6a2 10 to the power of minus 4 m2 pi 0.1 meter to the power of 2. So it will be equal to 8.68, and we don't have a number 8.68, so 9 number of tubes. Okay, so here, but you might ask this question that AC is cross section area, while AS we said that is a surface area of heat exchanger, if you remember. So surface area of the heat exchanger. And AC is the cross section area. So why we use that in this specific correlation or question interchangeably? So we basically put that replace that AC with AS. Why that? Why is that? Is because of this particular question. In this particular question, the cross section area is equal to surface area of the heat exchanger. But is it the case in every single geometries and situations? No. Okay, so just keep it in mind that AC is the cross section area and AS is the surface area of the heat exchanger. A basically is area, but in different fields or topics that we are talking in heat transfer, it might have a little bit or a slightly different meaning. Just keep it in mind that when you are calculating the area, be aware what kind of area are you calculating. Is it cross section? Is it surface area? Give special attention to it. I think that's enough for today. Next week basically we covered all the material necessary for MHM 420-780, and next week we are just going to solve some example, and the last lecture will be a kind of like a question and answer session. So it will be an online session. If you would like to come online and ask any kind of question regarding the course, you are more than welcome to do so. You can find the link to the Google Meet online meeting on ClickUp. But before that, on Monday I'm going to solve another example together, and on Tuesday we are going to have online meeting, and that will be our last session before the final exam. Thank you so much for your attention, and see you next week. Bye bye.